Okay, so now we're going to move on to chapter 17 and part of 16. We pulled this part of 16 out because it deals with equilibrium, which is not something that is taught in chapters 15 and 16. It's actually taught in 17, so it's a little bit odd how the book is set up. So we kind of picked and choose what we wanted to do. So we're going to talk about something called kinetics and equilibrium. So kinetics is a pretty short topic, and it deals with something called the collision theory. The idea behind a chemical reaction is in order for chemicals to react, they have to bump into each other. Okay, I'll do some demos for you to see how this works. They have to come in contact with each other. They have to collide. That's the term. As they're moving along, remember, gases have a lot of kinetic energy, and they're moving, and as they move, they can bump into each other. And what we want is we want molecules to bump into each other so that they can react. And the reason why is they have to have their old bonds, remember our Lewis structures, they have to break and new ones have to form. So for example, I'll just pick the most common example. Hydrogen, oxygen goes to water. Okay? You have to have those hydrogen molecules bump in here. Hydrogen looks like this. Oxygen looks like this. And they have to break these old bonds, and then they have to form new ones to make water. Okay? They have to collide, and they have to collide with a decent amount of energy, but the more often they collide, the more likely it is that they're going to react. And a lot of times you'll see me do a chemical reaction, I'm like, oh crap, it's not working, let's add a little bit more. Let's see what happens if I add a little bit more. And because I'm adding more, that means there's more molecules in there. And if there's more molecules, the odds of them colliding with each other are greater, and the odds of the reaction happening are greater. So basically, for any kind of a reaction, if you increase the concentration, that would be the molarity, you are going to increase the rate. If you're talking a gas, we're talking about increasing the pressure. Okay? There's more opportunities for them to collide. Think about it at a molecular level. For a solid, though, solids are a little bit weird. What you want to do is you want to increase the surface area, okay, and stir them up. And the reason why is if you have a solid that's a cube, okay, the molecules that are in the center of that cube can't interact with something outside because they're trapped in the middle. But if you increase the surface area and you turn it into a bunch of little tiny powdered crystals, then all of them have the opportunity to react, and therefore there's more chances for collisions. Stirring them up, more chances for collisions. For a liquid and a solution, basically you want to add more. Stirring it up helps too, because you're, again, providing more opportunities for collisions. For a gas, though, like I said, you want to increase the pressure. You want to push them closer together so they're more likely to bump into each other. Or decrease the volume. Remember Boyle's law. Pressure and volume are inversely proportional. Same idea. Okay? Second part of the collision theory is that the molecules have to collide with sufficient energy to break reactant bonds. It takes some energy to break those electrons apart. If I have oxygen, my God, that's a double bond. And I'm trying to break that apart, I have to put in energy to push those electrons away from each other in order for them to react with hydrogen. So if you increase the temperature, that will affect the rate greatly. They'll react faster because, for two reasons. Number one, they have more collisions. They're moving faster. Okay? Increasing temperature makes those little molecules bounce around. Think back to that simulation we did with the gas laws. Okay, the little guy in the scuba tank. If you heated that thing up, those little particles were bouncing around like crazy. Okay? More collisions means more opportunity for them to react. And not only do they have more collisions when you increase the temperature, but every time they hit harder. And if you think about this with regards to, say, in a car. If you're in a car and you're going 5 miles an hour and you bump into another car going 5 miles an hour, yeah, you're going to do some damage. There's some energy associated there. But if you're going 50 miles an hour and the other car is going 50 miles an hour and you bump into each other, there is greater energy associated with that collision. And that means, with regards to chemicals, the odds of them having enough energy to break that bond are greater. And so, as a result, you'll get a higher or more faster rate of reaction, greater rate of reaction. The third rule for the collision theory is that the molecules must collide in what's called the correct orientation, or it's called the steric factor. You don't really need to know that, but they have to line up properly, and I'll show you an example of what that looks like. And it's due to the way the molecules line up in order to break those bonds, and I'll give you an example with this. Okay, that reaction. So I have to take two BRNOs, and they have to bump into each other properly so that they can turn into Br2 and NOs. Okay, so I'll show you a little picture of what that looks like. So here's my two BrNOs, and they're going to turn into Br2 and 2 NOs. Now if they collide right here, it is possible that they could collide with enough energy to break that bond and reform a new one right here. You get bromine and then the 2 NOs. Okay, so that's a correct steric factor, a correct orientation. If they line up like this and they bump in right here, it's possible they could break the bonds and reform it here, and you will get Br2 plus 2 NOs. However, if they lined up, that would be a correct orientation. If they lined up like this and they bumped right here, those Brs are so far away from each other, they're never going to form a bond. And the NOs, I mean the Os could potentially form a bond of some sort, but the Br2, I'm not going to get Br2 and 2 NOs. This would be a steric factor or an orientation that is not conducive to reacting better or producing a greater rate of reaction. So some important definitions for you. The first one is activation energy. This is a really important definition. It's probably the most important definition in the chapter. It is the minimum amount of energy needed when they collide to make that reaction happen. If they don't have that, they don't break those bonds. If they don't break those bonds, they don't react. Okay? The bigger that activation energy is, the slower the reaction is, because it takes a lot of energy to break those bonds. And it's all about energy and temperature. As temperature increases, they're going to collide harder and harder and harder and harder. And how they have to line up. If they only have like one way that they can line up and form the products, then it's going to have a high activation energy. Okay, the activated complex, that is the way when they collide. If I had the BrNO colliding with the ONBr, that is an activated complex. There's no such thing in the real world as that, but it's like the moment they collide, boom, at the moment they collide. Just like two cars, when the minute they hit, that is a activated complex. Okay, it's not something you would normally buy in a car, in a store. You can't normally go out and buy two cars smashed together. Okay, you buy them individually, and that's what this is. It's kind of the idea is the two molecules come together and form this weird thing. Okay, and it's kind of, it's imaginary almost. It's a transition state. It's what happens when they actually collide. And then we're going to talk about these energy profiles. And what they are is they're a graph of the energy that's involved versus basically the time. They call it the reaction coordinate, but basically coordinate means axis. And so along the bottom it's the reaction axis. And it's basically to show you how the reaction proceeds in terms of energy of the products, the reactants, and the activated complex. Okay, this is what one looks like. So here's my BrNOs and my BrNOs. These are my reactants, and these are my products. Okay, they have, if this is 0, this is as time goes on. My reactants have a certain amount of potential energy, just based on the way they exist. Whatever it is, if that's 0 up to whatever this number is, let's say it was 100, then the potential energy of my reactants is 100. My products, measuring from 0, have a certain amount of potential energy as well. Okay, and if it was, say, that was 50, if you draw a line all the way across, let's say that was 50, this was 100, potential energy of my products would be 50 minus 0, 50. Okay, so they have a certain amount of potential energy as well. When they come together and they collide, they form this thing called the activated complex. But like I said, it's not something that normally exists. You can't go to the store and buy it. It actually has quite a lot of potential energy. Okay, as an activated complex, the potential energy is quite high because it doesn't normally exist. It's the moment of collision, boom, they hit, and at that moment when they hit, they create this molecule, this transition state that doesn't normally exist. It has very, very high potential energy. If that's 0, and maybe this is, 300 up here, it has a potential energy of about 300. Much higher than either my reactants or my products have initially. Now, in order for my reactants to turn into that guy, I'm going to erase the ink on this slide here. In order for my reactants to turn into my products, they have to collide. And when they collide, they have to turn into that guy. In order to turn into my products, eventually, they have to turn into this. They have to collide. Now, I want you to think about it this way, okay? Let's say I'm standing here, here's me, with a bowling ball, and I want to get the bowling ball over the hill. Now, if I roll that bowling ball up, and it only makes it right here, it's not going to make it over the hill. It doesn't have enough energy to get over the hill. It's going to roll right back down. Okay? But if I take that same bowling ball, okay, here's me with the little bowling ball, and I give it enough energy to get it over here, it's going to go down the other side. Okay? Because I gave it enough energy to exceed that energy that's required to get to the top of the hill. I gave it enough energy to get over the hill, and it's going to turn into the products. Now, I want to use that analogy when I'm talking about my reactants. My reactants, to turn into my products, they have to turn into this guy. They have to collide and turn into him. And in order to do that, they have to gain a certain amount of energy, just like my little bowling ball did. They have to gain a certain amount of energy to turn into that, because that potential energy of the activated complex, remember I said it was like 300, and these guys were at 100? They have to gain, let's say it was 200 joules of energy in order to turn into that. Now, once they turn into that, then they can turn into my products. But for right now, they have to gain that much energy to become that. If they don't gain 200 joules of energy, let's say they only gained 150, well, they go this far. Well, come right back down. No reaction's going to happen. It's just like my bowling ball that doesn't have enough energy. So they have to gain enough energy to get to the top of the hill, and the term for that is the activation energy. The difference between where my reactants start out and where my activated complex lives, or my transition state lives. They have to gain that much energy, and it's called the activation energy, in order to turn into that. And once they turn into that, then they can turn into the products. They could potentially go backwards too, but they could turn into the products for sure. That's the only way to do it. Now, we have talked about delta H before. I know it was in January. It's been a long time. But if you remember, delta H is the products minus the reactants. And in here, it's the difference between where the products are and the reactants are. Here's my reactants. Here's my products. This one would be an exothermic reaction because the products are at lower energy and the reactants are at higher energy. Remember I said this was like 50 and this is 100. So if I do 50 minus 100, I get a negative number, negative 50. So remember, exothermic is a negative value of delta H. So that's what an energy profile looks like. You've got reaction coordinate, which is basically time, along the bottom. You have potential energy over here. It always starts at 0. And you always have a hill. Okay, the hill can be big or it can be pretty small. It's just a matter of what the reaction looks like. Now, catalysts you guys have heard about in biology. Catalyst speeds up a reaction without being used up in the reaction. You guys probably talked about lactase, or that's the biggest one I can think of, is lactose, because you can't digest milk sugar. There's other ones too. You can't digest proteins. I don't remember what the names for those are. But anyhow, they speed up a reaction without being used up in the reaction. And in chemistry, we have chemical catalysts. They are either homogeneous, meaning they're the same phase as the reactants, so they're either dissolved in water, or they're a liquid, or they're a gas, or whatever, or they're heterogeneous. And most of the ones that I'm familiar with are heterogeneous, meaning it's a solid and you're adding it to a liquid, or it's a gas and you're adding it to a liquid, that kind of thing. It's just, they're not the same phase. Okay, how do catalysts work? Well, the way they work in chemistry, and on the chemical basis of it, they allow the reaction to proceed by a different mechanism, a new pathway. In other words, they change that hill. They make that hill different. It's almost like they tunnel through the hill. They give it a different mechanism to make it happen. It predominantly affects the ability of the steric factor. It makes them better. They make them collide better. And what that does is the new pathway has a lower activation energy. In other words, the hill is smaller. Like I said, it tunnels through the hill. And therefore, more of the molecules can get over the hill, and the rate will increase. Let me give you an example of this that maybe you've heard of before. If you've ever heard of a catalytic converter, they are in cars, and one of the things that comes out of your car's engine is carbon monoxide. Okay, carbon monoxide is bad. Carbon dioxide is bad enough. Carbon monoxide is much worse because it's a poison. It'll kill people. And the reason carbon monoxide comes out of your engine is because you're burning octane, and there isn't enough oxygen in your engine to react with all of that octane and produce carbon dioxide, which has its own issues. So a lot of the stuff that comes out of your engine is carbon monoxide, which is a gas. What a catalytic converter does is it's at the end of your engine, it's at the tailpipe, essentially. It's right before the tailpipe. And if you look on the inside, it looks like a sponge. And what it does is it takes that carbon monoxide that comes out of your engine, and it allows it to react with more oxygen, and it's going to produce CO2. Okay? It takes two of the carbon monoxides and reacts with an oxygen and produces carbon dioxide. Okay? So it allows the reaction to proceed because it gives it the sponge area. And these are all gases, and it gives a place for them to collect and helps them collide. Because they're gases. Gases don't collide well to begin with. And by giving it this sponge area, it gives it a new place for it to collide. It lowers the activation energy, and it produces CO2, which has its own issues, but at least you're not producing carbon monoxide out of your gas tank. Not as much, at least. As long as you have a high concentration of oxygen around, and as you're driving, you generally do, it'll produce carbon dioxide. So what a catalyst does is it provides this new pathway. It lowers the activation energy. It doesn't change the reactants, and it doesn't change the products. It doesn't change the delta H. All it does is change the hill, makes the hill smaller. They are initially listed as reactants, but then they're produced in the exact same form as products. They're not intermediates, and I'll talk about what a mechanism looks like in a minute. So what a catalyst does is it literally changes the height of the hill. It doesn't change where you start, and it doesn't change where you end. All it does is make the hill smaller, and it lowers the activation energy. For a catalyst is much lower. That's all it does. Okay, so what I want you guys to do is go through this, identify all these various different concepts that we've been talking about. Reactants always start here, products are here, and this is your activated complex at the top. Okay, so the potential energy of the reactants goes all the way to the bottom. Remember, this is 0. The potential energy of the products also goes all the way to the bottom. The potential energy of the activated complex also goes all the way to the bottom. Okay, activation energy for the forward reaction. So here's my reactants. In order for them to react, they have to get to the top of that hill. Activation energy. Now, sometimes we're going to start talking about reversible reactions. Sometimes reactions go backwards. And in this case, if my products had to turn into my reactants, they have to climb a hill as well. This is the activation energy in reverse. This is the activation energy in the forward direction. Now, I'm going to add in, I'm going to erase what I've got, and I'm going to add in a catalyzed reaction. It doesn't change where you start, and it doesn't change where you end up. Okay, so like I said, when you put a catalyst, it doesn't change where you start, doesn't change where you end up. All it does is make the hill a little bit smaller. And what you end up having is an activation energy that is a little bit less than the original one because it has been catalyzed. It makes it a little bit easier for those reactants to turn into those products. Okay, so that's the activation energy for the catalyzed reaction. Overall, is it exothermic or endothermic? Well, that is referring to the delta H. The delta H is the difference between where the reactants are and where the products are. And as a result, if you look at this, my reactants start with very low potential energy. My products have very high potential energy. In order to turn into products, I have to gain energy. In other words, it is endothermic. All it does is make that hill smaller. Okay, so now reaction mechanisms are a little bit strange. They're similar to what we were doing with Hess's law. What they are is a series of steps that actually take place in a chemical reaction. So the reaction doesn't happen in one step necessarily. It might happen in more than one step. And the reason why it exists is because it tells step by step how the reactants collide and eventually form the products. Because remember, that's the collision theory. The reactants have to collide in order to break their bonds and form the products. Now, there is a rule with regards to reaction mechanisms. You're not allowed to have more than 3 reactants collide at one time. And the reason for that, I want you to just think about this from the point of view of cars. If I had 5 cars out in the parking lot, in the senior lot, And I said, all right, guys, we're gonna collide all 5 of these cars together at the exact same moment. Not 2 cars collide and then the 3rd and 4th and 5th car hit in turn. No, all 5 of them have to hit at the exact same moment. So even if you were very good and all the other people driving in the car were very good at it, the odds of all 5 of those cars smashing at the exact same moment is really, really unlikely. And for the point of view of a chemical reaction, the same thing is true. It's really, really unlikely to have more than 3 reactants hit at any one time. They could potentially collide into each other, maybe, but they don't stick very long. So that's the thing. It's not like a car. It's not like they can collide and stick and then another 3rd one hits. It doesn't work like that. So the rule for reaction mechanisms is you're only allowed to have really 2 reactants or maybe 3 in any one step that's involved in a reaction. And the kinetics of a reaction can tell us the mechanism. If you take AP Chemistry, you'll learn that. But for right now, what you guys are going to deal with is the mechanism that they give you, and you won't have to create them, must describe the stoichiometry of the overall reaction as well as the order of the steps of the reaction, meaning you're only allowed to have 3 at the most. So here's a reaction that occurs spontaneously. If you look at this, I have 5 molecules that must collide at the exact same moment. Well, that doesn't make any sense. So somebody came up with this idea of a mechanism. And they said, all right, here's the idea of how this one happens. It's like a domino effect. One of the HBRs collides with an oxygen and forms this thing called Huber. Now, Huber's a made-up molecule. It's certainly not part of my reaction up there. Huber then turns around. So this is the first step. And in the second step, a Huber goes out and finds an HBr and forms 2 Hobers. Okay? And again, 2 reactants collide, forms the 2 Hobers. And then in the 3rd and the 4th step, which really are the same step repeated, each of the Hobers goes out and finds an HBr and makes a water and a bromine. And so what you're going to see is you're going to say, all right, is this an acceptable mechanism? Well, I only have 2 reactants, and it's certainly possible for 2 reactants to collide in any one step. And does it add up to the stoichiometry? So this is where the Hess's law kind of comes in. What you're going to do, you don't have to actually do anything other than add them up and cancel things out. So if you notice, my Hobers, I have 2 Hobers on the left and 2 Hobers on the right. I have a Huber on the left and a Huber on the right. And I have 1, 2, 3, 4 HBRs and oxygen. I have 2 waters and 2 bromines. And so it works. That makes it an acceptable mechanism. Which 2 substances determine the rate? Now, this is where the kinetics comes in. Okay? If you look, you will always see one step that is listed as the slow step. The other steps are referred to as being fast. What that means is that step has a really high hill, either that kind or that kind, but it's got a really big hill. It takes a long time for HBr and oxygen to come together, break those bonds, and turn into Huber. It takes a long time for that to happen. But as soon as Huber is made, man, it's off and running, man. The rest of it happens almost instantaneously. But that first step, making the Huber, takes a really, really long time because it has a really, really big hill. So which 2 substances determine the rate? That would be HBr and oxygen determine the rate for the reaction because they are so slow that everything else is essentially instantaneous. So the amount of stuff that I have of this really determines the overall reaction just because they're so slow. Now it says, what are the formula of the intermediates? Well, those would be anything that you just crossed out. Huber and Hober. Okay, this is what it looks like if I did a potential energy diagram for these guys. It takes place in 3 steps. There are 3 different activation energies. This is the first step. Now this is not the same thing as the Huber and the Hober. This one is a very short hill on the first step. The second step is going to be a little bit slower because it has a high activation energy. That would be what's called the rate determining step. That would be the one that's the slowest one. The third step has a very small activation energy. The second step is what's called rate determining. In other words, it's the slow step. The activated complexes, these are the intermediates kind of thing. Oh, actually, those are not the intermediates. Those are what happens when they collide. The intermediates are here. This is where like Huber and Hober would be.